Well, welcome back to Python scripting for GIS applications. This is a class at the University of Alaska Fairbanks, and it's spring semester 2013. From last time, your assignment was to write an Arcpy script that will build a raster attribute table if it doesn't exist. So what we can do is first make some test rasters. So I made a sample text file called test.txt. Basically, we've got these keywords that the ASCII to raster tool will understand. So we'll have 3 rows by 3 columns, and then here's our data. And then we run the ASCII to raster tool using that text file, and we create an integer raster. So here we run the same tool, creating a floating point. Okay, so what we'll do is we'll get a list of rasters in our current workspace. So then we'll see how many rasters we have in this list. So we've got 2 rasters in the list. So then what we want to do is for each raster, determine if it's an integer raster, and then if it's an integer raster, determine if it has a raster attribute. So we'll make a raster object from the first raster in our list using the raster function. And then we can look at some of the properties of this raster object. So what's the pixel type of this first raster object? So the pixel type is F32. So we could print that pixel type because it's a string. So it's floating point 32-bit. So it's not possible to create a raster attribute table if a raster is a non-integer raster. So then we'll do the same thing. What's the next raster in our list? So that would be index 1. And then what's the pixel type of that raster object? So this is a pixel type short integer 32-bit. So we can build a raster attribute table for this raster, but it may already have a raster attribute table. So if we look at another property, does it have a raster attribute table? So has raster attribute table. And in this case it does, so there's no need to build the raster attribute table. If that was false, then we would build a raster attribute table for that raster object. So one problem deals with LIDAR data, and here's the final script tool that you would develop where the user would input the first return LIDAR elevation raster, the last return LIDAR elevation raster, and then a threshold for canopy height representing tall trees. And then the script tool will output tall points, so any pixel point that has an elevation above 30 meters. So I'll show you how that works. Okay, so basically we have 2 rasters, and the last return is the last return from the laser. So basically it's where the laser is hitting near the ground surface and then returning all the way back to the airplane. So that's going to represent our ground elevation. So we'll make a raster object from that last return string. And then the first return is the first return from the laser, so that's typically at the top of the forest canopy. So we'll call this top canopy raster. So if we have the elevation from the top of the canopy and we have the elevation at the ground surface, if we subtract the 2, that would give us the elevation of the canopy, so we can just subtract the 2. So we'll call this height raster. So that's going to be equal to our top canopy raster minus our ground raster. So what's the average canopy height for this area? So the average canopy height is about 2.3 meters. And what's the minimum canopy height? It's a negative value. So this is a bogus value because the minimum canopy height should be 0. It should be pixels that were just ground surface with no plant canopy. So this is just due to basically system error. And what we want to do is eliminate those pixels that have a value less than 0. So we can do that using the set null tool. So I'll make another raster object, and then we're going to use set null. So with set null, it's going to ask a question about an input raster. So our input raster is our height raster, and then comma. And then if the question's false, what do we want the pixel values to be? So if the question's false, keep the pixel values. And then we have our question. So our question is the pixel value less than 0? So if it's less than 0, eliminate that pixel, make it a no data pixel. If it's 0 or greater, retain the canopy elevation value. So now if we look at our canopy raster, what's the minimum value? It's 0. And then if we look at our canopy raster, what's the average value? It's about 2.328 meters. And what's the tallest pixel in our area? So it's 34.6 meters. Okay, so what we want to do now is isolate tall pixels. And that's going to be a user-specified threshold. So I'll make a variable height threshold. And let's say that's going to be 33 meters. So we want all the pixels that have a canopy height 33 meters or greater. So value less than, and then we're going to take that height threshold and convert it to a string. So if we look at my query, it now contains that string. Okay, so then we could, once again, create our tall pixels raster. Use the set null, and we're going to ask questions about our canopy raster. And if the question's false, keep the pixel value, and if it's true, make it no data. So then our my query is going to be the query. So any pixel less than 33 meters becomes no data. Okay, you notice tallpixels.catalog path, it doesn't return a catalog path because these are all sort of temporary scratch rasters. So if you ever want to save any of these rasters, you'd have to basically use the raster object and then .save. So then .save, and it would save it to the current Arcpy environment workspace. So I'll save this as tallpixels.tiff, and that actually saves that raster object to the hard drive. If I don't save it, then these raster objects are just raster objects that are in your default geodatabase. So they're sort of just scratch raster objects in your geodatabase. So I'll save it just to be safe. Okay, so it's a lowercase save. So that saves that to your hard drive as a raster named tallpixels.tiff. Okay, and then our final step is we convert our raster object to points. So that would be Arcpy raster to point. And then it needs the input raster, which is this raster. So Control C, Control V, and then whatever we want to name our output. So our output, I'll call it, and then we can look at the result in Arc. So here we have the ortho photo of the study area, and then the last return representing the ground elevation, and then the first return representing the top of the forest canopy. And then basically we have our tall points, and those are pixels where the top of the forest canopy was at least the threshold value the user set or above.